So we're going to talk about this optimization in detail in the optimization chapter, but basically let me explain how this optimization, how training works. Let's say this one is objective functions, and then we have one single parameter w. Okay, again in the neural network we have a lot of parameters. In the matrix we have lots of parameters. Right? When we focus on the one single parameter w, then we can start from one random initializations. So let's say the random initialization is around here. Then we can take a derivative. If the derivative is positive, okay, so in this case derivative is positive, then we have to go to the left side. So we have to move to the left of this w. So if we move slightly, then compare this value and this value. From this to this, we minimized this loss function. It's better. Okay. And then now we are here and we take a derivative one more time. Okay, this one is positive and we have to move toward the left side. And now we take a derivative one more time and positive and we move. And now when we take a derivative, oh, this one is negative, then we have to move to the right side and it converges around here. Okay, if we start from here, okay, then we do the same thing. So take a derivative and the derivative is negative, then move to the right side and take a derivative and it's negative, move to the right side and again and again and again, and it converges to this one. So it converges to local optimum. Okay, so we cannot find the global optimizations. If we can find it, is lucky. But in general, as I said, neural network is not a convex problem. So we can get stuck in the middle of local minimum. But usually, many times, local minimum is as good as global minimum. So don't worry. The problem is usually it's hard to get local minimum. Okay, so we're going to talk about all these optimization issues in the next chapter. But anyway, so based on this gradient, then we can update one parameter. Then what if we have 1,000 parameters in the neural network? Then we apply this one 1,000 times. Okay, that's the beauty of this partial gradient. When we focus on single parameter, then we ignore all the other parameters. So we just update one parameter and the next parameter and the next parameter. Usually we do this in parallel. Okay, so because all the parameters are kind of independent in this approach. And long time ago, we had to implement this backpropagation by ourselves, but now you're lucky to have these automatic differentiations. So instead of implementing these backpropagations, as long as you define this for the propagation, then they will calculate the backpropagation for your benefit. Okay, so you are lucky to have these softwares. Oh, by the way, at the beginning of this deep learning era, Theano was the only option. And then Facebook provides PyTorch and Google provides TensorFlow. So let's compare this neural network to RBF networks. In the RBF networks, we have radial basis functions like this, and then we represent the input in this space, and then these are not the trainable layers, and then we have one trainable layers here. So that is a linear regression. And compared to the RBF networks, in neural networks, the basis functions are adaptive. Okay, which means we can train the first layer, which means the basis functions are parametric. So instead of these basis functions, in RBF networks, these basis functions are fixed. The mean is fixed and the scale is fixed. But in neural networks, as you saw, to make this hidden representation, so this neural network, the parameters can be trained. And this one corresponds to one node in the RBF networks. This one is actually a vector. So given this input x, this x will be projected to this node and this node and this node. And this projection is based on these trainable parameters. So that's the big difference between these RBF networks and the neural networks. And the next one says neural network has the distributed representation. In the RBF networks, these basis functions are local functions. And when we have one input x, then the closest basis functions will work dominantly, right? But in the neural networks, that's not the case. So all the nodes in the hidden representation will work. So it will extract some features from this input, and this one will extract another feature, another feature, another feature. And the objective function is not convex of the parameters. In the RBF networks, we have only one layer which is trainable, but in the neural networks, all the layers are trainable. So this is not easy to train. So the function is not a convex function, so it's hard to train the neural networks. Again, but in the RBF networks, it is a linear regression on top of the fixed features. Okay, so the training doesn't take much time. So learning comes so quickly. Okay. And the neural networks are not biologically plausible. So we don't have this kind of systems and architecture in our brain. And biological realism is an unnecessary constraint, actually, and neural networks are efficient for statistical pattern recognition. That's it. So, there is a kind of figurative speaking about the plane. So, when we invent the plane, do we have to make a plane like a bird, or can we just accept the principle of how the bird flies? Then we can apply that principle to implement to invent a plane, which is flying in a different way, but based on the same principle. Likewise, when we implement neural networks, then we can get some hints from the biological neural networks, but we don't have to implement biological neural networks one by one. We don't have to implement everything. Instead, we can get some hints. As long as we understand the principles of how our brain works, then we can adapt those principles, and then we can invent new algorithms to simulate or to implement how our brain works. So the neural network is biologically implausible, but that's not a big problem. Okay, so as I said, a neural network is not biologically plausible. So Mike Davies said backpropagation doesn't correlate to the brain. It's really an optimization procedure. It's not actually learning. It's not just him. There are many researchers saying that the neural network is not actual learning. It's just adaptive machine. Okay, so in a sense, yeah, that's true. And even though backprop is mathematically effective, there is no natural example of it. Okay, so that's true. And in our brain, we have spiking neural networks. And there are some approaches and research directions to implement the spiking neural networks. And it's more brain-like and it is more energy efficient, but it's hard to train yet. There is no popular learning algorithms. So if you're interested in brain-like neural networks, then you can Google spiking neural networks. Okay, so we talked about the neural networks and with all the equations. And as I said, you don't have to implement backpropagation. So we can use some software like PyTorch. So here's one example of deep learning or neural network. By the way, the old implementations are based on Python and PyTorch. And we need to import some modules. Okay, torch dot something. And this one is about the data. Okay. And we define the neural network here. and it says, oh, I'm gonna use a GPU, and we have to define what kind of optimizer we are gonna use, and we are gonna use RMS prop, okay, and we will train. So when we use MNIST, then this is it. Then we have to talk about this model architecture and the training process. Okay, so we have model architecture here and the training procedure here. So in the neural network architecture, we have a couple of linear layers, and the MNIST image, the size of MNIST image is 28 by 28. So input is 784, and we use 500 hidden nodes for the first hidden layer and the 300 nodes in the second hidden layer. Then the question is, how can we define these numbers? There's no mathematical tool to define these numbers, or there is some fancy tool to find the better kind of these hyperparameters. Okay, so like Bayesian optimization, but that is way much beyond our class. So let's say we can just define these hyperparameters based on our gut feeling. Okay, but the first one should be 784, and the last one should be 10 because we have 10 classes. So we have to fix this one, and then the other numbers are your choice. But these two numbers should be the same, these two and these two. Okay, and then in the constructor, we define the network architecture, but in the forward propagation, we can make a connection, actually. So X is image, so we vectorize this image, and we applied first a fully connected layer, and then apply the hyperbolic tangent as a nonlinear function, and now we have X, so we applied the second layer with the hyperbolic tangent, so we have X, and so on. Finally, we got X, and then we apply the log softmax. And actually, we have to apply the softmax, but in the negative log likelihood, anyway, we have to apply the log function. So instead of applying softmax and log separately, then they have log softmax functions. Okay, and then in training functions, the first line says, oh, we are going to train this model. Okay, and then in this for loop, we get the one mini batch of the data samples from the train iterator, and we move this data and target into GPU and initialize our optimizer and apply the forward propagation and calculate the loss function and calculate the backward propagation and then update our parameter. That's it. So it's quite simple, right? So applying the deep neural network is really simple. Again, in this slide, just import some modules, and then we have to define your own data iterator. This part takes a lot of time if you have your own data set. And then we have to define the network architecture, and then we have to choose one of optimizers, and then we have to implement this training function. And training function is really simple, but in this function, probably you need some other kind of modules or lines to do something else. It's up to you. And the network architecture could be really simple, okay, but you can make a more complicated network architecture.